start Physics 100 students. Welcome to the second part of this week, Chapter 10. This is the last chapter for the second midterm. So the second midterm will be on momentum, angular motions, energy, and gravity/orbit. So you have one short answer question from each of those 4 areas for those 4 weeks. So this will be the last for the second midterm. The second midterm is not cumulative, so even though there might occasionally be a question where you have to use F equals MA, it'll deal primarily with the newest stuff. Our goal for this second lecture of this week, Chapter 10 lectures, is to understand orbits. Objectives were about projectiles at different velocities and how that leads to orbits. We're going to understand how orbits work. We're going to learn about escape velocity and how to be able to draw orbits too. Learn about escape velocity, Kepler's laws, and understanding our own solar system. So, I toss a ball. What is the shape of the ball? So let's just say I throw it horizontally. What is that shape going to be like? So if we're on the flat surface, there's me. I throw a ball, it goes like that. If I throw the ball a little bit harder, it goes a little bit farther. Because it's traveling faster, it takes some amount of time to hit the ground, but it travels further in that time frame. And so on and so forth. But suppose I throw the ball really hard, so that it goes a couple miles in the second it takes the ball to hit the ground. Now the motion is going to be a little bit different because over very large time distance scales, the Earth is actually curved. And so if I have a really high-powered cannon that looks like I don't know what that looks like, a beetle, and it shoots a cannon, there we go, shoots a cannonball, the cannonball will fly and then hit the ground. If I shoot harder, it will go further. But the further it goes, the Earth starts to curve down. I say it takes longer and longer for the cannonball to hit the ground, and so it travels further and further than if the Earth was flat. If I shoot the cannonball hard enough, the rate at which it falls will be equal to the rate at which the Earth falls. And if that occurs, that is the orbital velocity. Because then it will stay the same height above the ground, and it will always be falling towards the ground, but the ground will also be falling beneath it at the same rate. It turns out for the Earth, we need about 8,000 meters per second, about 5 miles per second, to achieve orbital speed off the surface of the Earth. Orbital velocity for any given object is equal to the square root, and it looks a little bit nicer over here. The orbital velocity equals the square root of this gravitational constant g, because it's based on the gravitational force, times the mass of the object that you are orbiting divided by your orbital distance, or orbital radius. Distance and radius mean the same thing. So now note that the radius is the distance to the center of the object. So if I'm orbiting the Earth 200 miles above the surface, I do not put 200 in for the orbital radius. I have to put in 200 plus the radius of the Earth, because that's how far I am from the center. So I'd have to use 4,200 miles instead of, and of course I have to convert that to meters, instead of just the 200. So always do if I'm orbiting an object, here's my object, and I'm orbiting it, I always have to take the distance to the center, not the distance to the surface. Very important. All right. So what happens if I'm in orbit? A nice, perfect circular orbit. Oh, by the way, this is an equation for a circular orbit, not an elliptic orbit. This only works for a circular orbit. Suppose I'm in my circular orbit and I speed up. What happens? So think about that for a moment. So this is my original orbit around the Earth, and then at this part here, I'm going to speed up. What is my new orbit going to look like? In fact, I want you to draw a picture like this and draw what the new orbit will look like in a different color and what your prediction is. So you probably either predicted something like this. So here's my original. Probably predict something like this, or something like that, or maybe some weird thing like that. None of these are correct, unfortunately. Now, the first rule of orbits is don't talk about orbit club. Second rule of orbits is you always come back to the point that you left from. Because it has to be an orbit, it has to come back to that point in orbit, otherwise it's not an orbit. So you're always going to come back to that point if you did something here. What's going to happen is it's going to change the other side of the orbit. So if I speed up, the other side of the orbit is going to move outwards. And so everything's going to move outwards towards that orbit, and then it's going to come back. The second rule of orbits is that when you have an elliptical orbit, the shortest distance and the longest distance have to be on opposite sides of what you're orbiting. I cannot have an orbit that looks like this, because my shortest sides are here, and my longest are there. That is not an orbit. All right, but this is very important. Now, you probably wonder, why is this important? Suppose an asteroid is going to come our way, and it crosses the orbit of the Earth. Oh no, it's going to hit us. It's going to kill all life on Earth. Well, lots of life. So here's our orbit, here's the sun, and here's the asteroid orbit. It crosses the Earth in two positions. So anytime it crosses the Earth's orbit, there's a chance it runs into the Earth. The chance is pretty small, it's about 170 million, but you do that every year for 35 million years, and you're going to run into the Earth eventually. Much like if you were to buy a Powerball ticket every single week, eventually you would win the Powerball. It would take about 100, it would probably take about 20 million years if you only bought one per week, but eventually you'd win. Actually, no, I think it's even worse than that. But if I catch the asteroid when it's here and I stick a rocket on it right there and I blast off the rocket engines and push it forward to make it go faster, its new orbit would be like this, possibly. And it no longer crosses the Earth's orbit. If it no longer crosses the Earth's orbit, it can't hit us anymore. So we can actually prevent an asteroid impact by using this trick. So we can prevent us going the way of the dinosaurs for the same reason. Gosh darn, we've got to have our own reason to become extinct, not the dinosaurs' reason. Elliptical orbits. Now, it turns out most orbits are not circular, they're actually elliptical. They're egg-shaped. I won't get any more than that in this class. If you want more about elliptical orbits, take an astronomy class. I teach plenty of those. The more you speed up, the more egg-shaped it becomes. If you do it too much, though, you actually escape from the system. Now the question is, how much do you have to speed up in order to escape? And it turns out it's not very much. It's only a factor of 1.4. Oops, I've given away the answer. Okay, so the orbit around the Earth is 8 kilometers per second. So let's say we have a rocket orbiting the Earth at 8 kilometers per second. We blast off our rocket that's in orbit around the Earth. How much do we have to speed up the rocket in order to escape from the Earth? Well, it turns out we only have to increase it by a factor of the square root of 2, which is 1.4. So we take 8 times 1.4 is 11.2. Now that's not how much we have to speed it up by, that's what we have to speed it up to. So if we increase our velocity by 3.2, so from 8 to 11, it escapes from planet Earth. In fact, it takes less velocity to go from Earth orbit to Mars than it does to get into orbit around the Earth in the first place. So once you're in orbit, you're already halfway there, even though you're only 100 miles up. It's kind of like if your remote control's on the far side of the room and you get up from your couch, you're already halfway there. Okay, not the best analogy. There we go. So 40% extra. So there's not a big range of velocities between orbit, a perfect circular orbit and escape. All right, our solar system. Let's. You can skip through most of this if it is very uninteresting to you, as I won't test you on most of this. However, you will need to stop at Kepler's third law. So Kepler's third law you need to know. You can skip to there if you want. Otherwise, an interesting historical perspective of our understanding of the solar system. 2,000 years ago, a man by the name of Ptolemy created a model of the solar system in which the Earth was the center and the Sun and all the planets orbited around the Earth. Now, this seems to be really crazy because it is not accurate at all. However, they actually matched the model to observations made at the time. Now, when they tried to make a perfectly circular universe, it didn't quite work for obvious reasons. So what they did is they had a little bit of a fudge factor. They called it an epicycle. So they had the Earth in the center, and they had the planets in orbit around the Earth, but the planets then had a circle within the circle that they went around as they went around the Earth. So instead of being like this, they were more like that. Some weird, funny shape because of the epicycle. And basically one epicycle per year. And it actually worked. It actually matched the observations and allowed them to predict the position of planets for the next 1,500 years. But after 1,500 years, the wheels fell off. The predictions no longer quite worked. They were off by a month or two. And it was a very cumbersome, very complex, very complicated model, and it was really hard to reform to make it better. And so people were beginning to realize that this was not the correct model for the solar system. A man by the name of Copernicus came around, and he tried to solve the problem by putting the sun in the center. And the reason being is that every year, if you watch Jupiter and Saturn, most of the year they go this way across the sky. But for about 1 month every year, they'll stop, turn around, and go back this way, and then stop and turn around and go that way. This is called retrograde motion. And so they had to explain the retrograde motions. They tried to do that with the epicycles. Well, Copernicus realized that if you use the sun in the center and everything orbiting the sun, if the Earth was closer to the sun than Jupiter and Saturn, then each year the Earth would pass those planets, and as the Earth passed those planets, they would appear to move backwards, even though they don't actually move backwards. You could get rid of the epicycles and just have a nice, neat model. And so he tried it, and it failed. Miserably. So he had to go to a second creation. So his first one was never published. He scrapped it. Take two, and action. He had to add back in the epicycles. And then it would work with the epicycles. But with the epicycles, its level of accuracy was the same amount as the Ptolemy model. And it was just as easy to use, as tough to use. So imagine that you hate your computer and you hate your operating system. And you go into the computer store and they go, well, we got this brand new system, this brand new computer. It's just as difficult and user unfriendly as yours. And it's just as costly as yours. And it's just as everything as yours. Are you going to use it, or are you going to use the old one? That's right, you're probably going to continue using the old one. So Copernicus's model failed on purely scientific reasons. The church had nothing to do about it, especially because he published after his death. Just in case. Then Kepler, Tycho Brahe came around, and he did some very accurate observations, because it would take very accurate observations to figure out exactly what was happening in our solar system. So he did that. Very accurate observations. The most accurate ever done without a telescope, because shortly afterwards they started using telescopes. And then his apprentice, Kepler, upon his deathbed, got his data, and Kepler was really good with theory. Tycho was really good at observations, but his theories were terrible. In fact, his model of the solar system was so awful that not even he took it seriously. That's when you know it's pretty bad. So if you ask an author how good is the book and he says it sucks, you know you definitely don't want to read it. Unless they're joking. And then you probably get one. By the way, my book sucks. So Kepler made the model, and he started with circular orbits, just like everyone else had done, because that was what was predicted 2,000 years prior. That was the assumption that had been made for 2,000 years, is that orbits were circular. And when he tried the circular orbit, it worked okay for most of the planets, except Mars. And for Mars, there were two spots where it was off, opposite sides of the sun, where it was off by 8 arc minutes. And the observations were accurate to 1 arc minute. So at this point, Kepler had a dilemma. And there was a few things he could have decided, all of which would have been perfectly valid at the time. He could have first decided that, you know what, I've got the right model. Tycho was the one that got it wrong. Tycho was a known drunk. In fact, he died early because of his excessive drinking. He could have said, you know what, maybe he was too drunk that night. His eyes played tricks on him. Or he said, you know what, I'm a little concerned by these errors. You know what, I got everything, all the other planets right, almost everything from Mars is right, except there's 2 points. It's good enough. I'll let someone else figure it out in 1,000 years. Or he could have said, no, this won't do. I'm going to throw out years of research, years of calculation, and start completely over. And any one of these three would have been a perfectly valid decision. But Kepler was 2 things. 1, very loyal to his mentor. And 2, he was a perfectionist. And so there's no way he was going to blame his mentor for the errors. And there was no way he was happy with these errors. And so he decided that the model was wrong and blew it up. He decided the error lied in the shape of the orbit. The 2,000-year-old assumption. What if that assumption was wrong? And that's the thing about science. We always have to question assumptions. Now, a lot of times assumptions are right. Sometimes they're wrong. And when they're wrong, we need to question them in order to see if this assumption is wrong, how does this play out? Does it play out differently? And sometimes, in this case, it did. So he changed the shape. He tried an oval first, it didn't work. He tried triangles and squares and all sorts of other weird shapes. None of them worked. Then he realized he made a math error when he tried the oval. Tried the oval again with the correct math, and it worked. So it turns out the error that everyone had made in calculating the solar system was that they were using circular orbits, and orbits are not circular, they're elliptical. Now for most planets, they're pretty close to circular. Not for Mars. Mars is very elliptical. And so orbits are elliptical. And the fact that he questioned 2,000-year-old assumptions and then used observations to tie in with this theory made him the father of the scientific method, the method that we use for science today. And then all science is based off of this. Even those you going into radiography or nursing, etc., you will be using this in your profession in some amount at some point in time. You'll notice patients' habits or patterns within patients, and you will infer something from that. And you'll use the scientific method to do so. And you'll question assumptions that are made by medical science sometimes, much like he questioned the shape of the orbit. So he came up with 3 laws. Why physicists and astronomers like to come up with laws and sets of 3, I don't know. But there they are. Law 1, orbits are not circular, they are elliptical. And I'm not going to really cover much of the rest of that. It's just a definition of what this is. You can read it if you want, pause it. I'm moving on to the next one. Law number 2, each second or day, if I calculate the amount of area covered in my orbit, those areas are equal, such that if I'm closer to the sun, I move faster. If I'm further from the sun, I move slower. This is an observation that he saw with the planets and seemed to be true, and he published those 2 in 9, that's important. The third law is the one that is really important for this class. And at this point, you should, if you're fast forwarding through this lecture to get to the important part, now is where you want to stop fast forwarding and start listening again. So this is the important part. Law 3, Kepler's third law. This is a law that allows us to calculate orbital periods of objects, which you'll be doing in this class. The square of the period equals a constant times this value called a to the third power. Now let me tell you what a is. There's a jargon term and then there's a easier way to explain it. A is called the semi-major axis. If you take the longest length of the ellipse, which is the shortest distance plus the longest distance, and take half of that, that is the semi-major axis. Now, that's the jargon term. The layman's term, easier to learn, and I put it down here. The period squared equals a constant times the average distance from the object cubed. So if you're orbiting the sun, you take your average distance from the sun cubed, times a constant, and that's equal to your period squared. Remember, that's the period squared. So to get the period, you have to take a square root. That's the average distance. Now, the way to calculate the average distance, if it's a circular orbit, the orbital distance is the average distance, you're done. If it's an elliptical orbit, you take the shortest distance plus the longest distance. They always have to be on opposite sides of each other. Divided by 2. Divided by 2. So it's fairly straightforward. So that means that if I want to go from the Earth, orbit the Earth, here's the sun, out to the orbit of Jupiter, I start here, I go halfway around the sun to Jupiter. And then the other half of the orbit would be back to the Earth. I have to go halfway around the sun, and this is my shortest spot, this is my longest spot. I cannot cross the orbits of the Earth or the orbits of Jupiter. That's how you draw these. Can't cross those two orbits, you're going between them, because this is my closest point, that's my furthest point, they're on opposite sides of the sun, and then my average distance is the average of this and that, which would be 1 AU and 5.2 AUs, which would be 3.1 AUs. So 1 plus 5.2 divided by 2. And then I can calculate the orbital period to go all the way around the sun, or I take half of that value, calculate the full orbital period, and then take half to determine how long it would take to go from Earth to Jupiter using that fuel. That's the most fuel-efficient orbit possible. Because that's how you usually go from point A to point B until you can have a spacecraft that are really insanely fast, which we currently don't. All right, so now the question we have to answer is, what's the value of the constant? So let's think about the sun and the Earth going around the sun. What is the orbital period of the Earth going around the sun? Now, to put that in layman's terms, how long does it take the Earth to orbit the sun? All right, now, do you want to square 365.25? Are you sure? Let's use a more straightforward number to do math with. How long does it take the Earth to go around the sun? Nice neat number. 1 year. 1 year. 1 is a nice number. How far is the Earth from the sun? Okay, well, this one's a little bit trickier because I haven't defined a certain value yet. It's 93 million miles, but do we want to cube 93 million? I don't. Do you want to take the square root of 93 million squared, or a cube? I don't. So let's define the value for the distance between the Earth and the sun. Let's create a new unit that defines the distance between the Earth and the sun. And let's call it an astronomical unit, an AU, so that the Earth is 1 AU from the sun. Now, if the Earth is 1 AU from the sun, and I cube that, and it's 1 year period, and I square that, what is the value, ignoring the units, what is the value of my constant? So 1 squared equals a constant times 1 to the third, the constant is 1. So if you're orbiting the sun, as long as you use your period in years, and your orbital distance in astronomical units, so we're not going to use physics units here, then your constant is 1. And then the period squared just equals the average distance cubed. So it's a lot more straightforward than. In fact, since I'm an astronomer, we get to use astronomer units. The orbital velocity around the sun, instead of using this big ugly equation here, actually works down to a much easier equation because the Earth orbits at about 30 kilometers per second. And so you take 30 kilometers per second divided by your orbital distance in astronomical units, and that gives you your orbital velocity around the sun. So for example, Jupiter at 5.2, you take the square root of 5.2, which is about 2.3. So 30 divided by 2.3, and that gives you your orbital velocity of Jupiter around the sun. We astronomers like to make the math easy. All right, so let's do a quick question. Multiple choice. You have an asteroid, semi-major axis at 4 AU, which means the average distance is 4 AU. This is a circular orbit. What is the orbital period in years? Go ahead and calculate that. Go. And the correct answer is, here is some stuff. So, period squared equals constant 1, if it starts to die, times 4 cubed. As long as I'm doing this in AU and this in years, I'm good. 4 cubed is 64. You can plug down your calculator. 4 times 4 is 16, 16 times 4 is 64. I take the square root of 64, that gives me my period, which is 8 years. That's all. Alright. Let's do another one. I don't think I have one on that slide. So I'm going to do, let's do the one where we go from the orbit of the Earth to the orbit of Neptune. Orbit of Neptune. So the Earth is 1 AU. Neptune is 30 AU. All right, so calculate the time you take to go from Earth to Neptune. Keep in mind that you're only going to do half of the orbit to get to Neptune. Now, don't divide by 2 until the very end. All right, so the first thing you're going to need to help you out is you're going to need the average distance. And then the total period, and then the travel time. So that's your pathway to solve this problem. There should be a few. All right, so go ahead and do that. Go. All right, average distance is the longest plus the shortest divided by 2. So that's 15.5 AU. That's my average distance. Now, the total period, period squared equals 1 times 15.5 cubed. I'm going to round this to 16 just because it turns out my period is going to be about 64. Now, I'm going to lower it by a little bit. Now, we'll just call it 64. Or we'll call it about 60. We'll round it to 60. Because I took this to the 3/2 power, which is this times the square root of that. 16 times the square root of 16, which is 4. This is 64, but right, that's a little bit less, so 60. That's the total travel time if I went out to here and back. Now, please note, when we do this, we cannot cross the orbit of Earth, we cannot cross the orbit of Neptune, and we have to go halfway around the sun to get to Neptune, and then halfway around the sun to get back to the Earth. But if I'm only doing this leg, I'm only going halfway, and so my total travel time to get to Neptune from the Earth using the most fuel-efficient route possible is 30 years. So without gravity assist from Jupiter, it takes 30 years to get to Neptune, which is why we don't send a whole lot of space probes to Neptune. All right. Then I'll give you more practice in class to do these problems. So to wrap up, orbits are fun and not as complicated as you might expect. If you change an orbit, it only pushes the other side of the orbit. This allows us to get to other planets and allows us to calculate a whole bunch of stuff. We're going to have a little bit of fun in our recitation this week. We're going to play the space race. or the homework this year. I haven't figured out yet which one I'm doing it because I had 6 months to make that decision. Weird thing about doing this before fall semester for spring semester. So I know I'm wearing pants in the middle of August. It's weird. Okay, but although for us when you're taking this class, it's freaking cold outside. All right, so just wear two hats. You'll be fine. But that's all for this lecture, and midterm coming up. Hopefully we'll do well on it. Just make sure you're good on momentum. Momentum's going to be the toughest one on this next test. The rest of it is fairly straightforward. So good luck. Over and out.